Hi everyone, welcome to our first video on matrices. Not matrices, matrices. Matrices is a plural form of the word matrix. And a matrix is a rectangular array of cells. So what does that mean, Mr. Kukla? Well, it means that you've got a box with a bunch of little boxes in it, and you can put stuff in these little boxes. These little boxes are called cells. And since these cells are arranged in a rectangular shape, we call this a rectangular array of cells. Now, you can put all kinds of things in these cells. You could certainly put a veggie wrap or a ham sandwich in a cell, but more often in math, we put things like functions in cells or classes of numbers in cells, but really those are upper college, I'm going to be a math major kind of things to put in cells. Usually the only thing we'll see in a cell is a number. -5, 2, 7, 1, -1, 3. And so we'll just see a bunch of cells in a rectangular array, and we'll call that matrix. Notice the matrix brackets, and when we write a matrix or when we read a matrix, we don't usually see the cells, we just see the numbers. So 3, 4, -1, 2. There's a matrix. Okay, and each of these numbers is in a cell. Now, we can talk about matrices by giving them a name, which is always a capital letter. Here's matrix A. Let me introduce you. We can also use a quality to describe matrices. There's two qualities we're going to be focused on today. We're just going to talk about order. And the order of a matrix is its rows by columns. So this one has 1, 2 rows and 1, 2 columns. So this is a 2 by 2 matrix. A 2 by 2 matrix because it has 2 rows and 2 columns. Okay, so how about here? This one has 1, 2 rows and 1, 2, 3 columns. 2 by 3. This is a 2 by 3 matrix. What about this matrix? What would this one be? Why don't you pause the video and give this one a try? Okay, welcome back. This is 3 rows and only 1 column. So this is a 3 by 1. As opposed to when the array goes this way and we have only 1 row, but 1, 2, 3 columns. This would be a 1 by 3. It's really important to tell the difference between these two, especially for the purposes of matrix multiplication that we're going to be talking about today. Okay, so we've got 3 by 1 because it's got 3 rows and only 1 column, and 1 row and 3 columns, a 1 by 3. All right. So what can we do with matrices? Well, the first thing I want to say is you can claim 2 matrices are equal to each other. So if I have 1, 2, 3, 4 equals 1, 2, 3, 4. These matrices are very clearly equal to each other because what's in this cell is in this cell, and what's in this cell is in this cell, and what's in this cell is in this cell, and what's in this cell is in this cell. In order to be equal, 2 matrices, in order for 2 matrices to be equal, everything in each corresponding cell has to be the same. Now, if I change matrix B to be 4, 2, 3, 1, all the objects are still in the box, but they're not in the right order, so these matrices are not equal to each other. Okay? What about this matrix? 1, 2, 3, -4. Are these matrices equal to each other? They are not equal to each other. Even though these are the same and these are the same and these are the same, these are not the same, and therefore these matrices are not equal. Everything in corresponding boxes has to be corresponding cells has to be the same in order for matrices to be equal. Okay. Now, if that's so obvious, what do we need to do? Well, so you may run into a problem that looks like x -2, 7y equals -4, -2, 7, 22. And then the directions say find x and y so that the matrices are equal. Well, if the matrices are equal, then the stuff in the corresponding boxes has to be equal. So x has to equal -4 and y has to equal 22. I know, you think that's so obvious, and yet when I put this question on the test that I gave last year for this, most students, or at least half students, left it blank. So it must get a little more complicated here. Let's try this one. 16, 4, 5, 4, -3, 13, 15, 6, 0, 2, 4, 0 equals 16, 4, 2x plus 4, I'm sorry, 2x plus 1, 4, 2x plus 1, and then 4. And then we've got on the second row -3, 13, 15, 3x, 0, 2, 3y minus 5, 0. Okay, so, yeah, what can we do here? Well, here's what I notice. These are the same, these are the same, these should be the same. 5 should equal 2x plus 1. So 4 should equal 2x, or x should equal 2. Now, I see another x over here. What if I had taken this and used those two corresponding cells? I would still get x equal to 2. So that should be straightforward, and then I need to solve for y. Here's y stuff, and here's y stuff, corresponding box. 4 equals 3y minus 5, 3y equals 9, y equals 3. So x equals 2 and y equals 3 gives us those matrices being the same. All right. Now, what else can we do besides say two matrices are equal? Well, we could do something called scalar multiplication. And scalar multiplication is sort of like that a value in front of the quadratic, or that c times f of x transformation we talked about last semester, or even 2 sine x. This is a stretching or compressing factor. That's what a scalar does. It stretches or compresses things. So scalar multiplication is where I take a constant and I multiply it times the matrix. To do that type of scalar multiplication, as opposed to matrix multiplication, which is where I multiply two matrices together. This is matrix multiplication. We'll talk about that later. This is just scalar multiplication. Scalar multiplication is just a matter of distributing the scalar to each of the values. And so we end up with 3, 6, 9, -3. Scalar multiplication is pretty straightforward. Here, why don't you try this one? Okay, pause the video, do that scalar multiplication. Welcome back. So when I apply this scalar to this matrix, I get -2, -6, +8, +4, +6, -14. There, scalar multiplying. No problem. ACT? Nah, they are not afraid to ask you about scalar multiplication. Well, in addition to scalar multiplication, we can also add matrices. But there's a requirement. In order to add matrices, the matrices must have the same order. So, for example, if I have this 1, 2, 3, this 3 by 1, and I want to add it to this 1, 2, 3, 3 by 1 plus 1 by 3, I can't add them because they don't have the same order. And so all I can do is say, sorry, I can't add you. Okay, so if they do have the same order, how do I carry out addition? Well, carrying out addition when they have the same order is pretty easy and straightforward. 1, 3, 4, 7, -2, 0, 5, -1. In order to add matrices, all we have to do is add the corresponding cells. So top left cell plus top left cell is going to give me 1 plus -2. And top right cell plus top right cell is going to give me 3 plus 0. And bottom left cell plus bottom left cell, 4 plus 5. And bottom right cell plus bottom right cell, 7 plus -1. And so I end up with -1, 3, 9, and 6. Adding, pretty easy, pretty straightforward. Subtracting works the same way. So let's call this adding and subtracting matrices. As long as the matrices have the same order, I can subtract what's in the corresponding boxes. What's in the corresponding cells. 1 minus a -2. Watch out for sign mistakes. So that's going to be 5. 2 minus 1. 3 minus a -3. 4 minus 6. Subtracting, done. We could even combine scalar multiplying with adding and subtracting. So, for example, 2, 3, 7, -2, 1, minus, let's do plus, 3, 1, -4, -1, 2. So I want to add these two, but I need to do the scalar multiplying before I do the adding. Okay? So let's apply the scalars, and so we'll end up with 6, 14, -4, 2, plus 3, -3, -12, 6. And now we can carry out the adding by adding what's in the corresponding cells. So we're going to have 6 plus 3, 14 plus -3, -4 plus -12, and 2 plus 6. And so we get this nice 2 by 2 matrix. The nice thing about adding matrices is you start with the same matrix and you end with the same matrix. If you start with 2 by 2s, you're going to end up with a 2 by 2. If you start with a 3 by 2 and a 3 by 2, you're going to end up with a 3 by 2. Okay, so what if we change this problem slightly and ask you to do it? 3 minus 2. Okay, pause the video, give this one a try. This is about as hard as we get with these basic operations. Welcome back. So I'm going to first apply the scalar by distributing that 3 everywhere. So now I'm going to have 9, 21, negative 6, and 3, minus, and I'm going to apply the scalar 2 everywhere. I guess you could apply negative 2 and then add these if you like. But that kind of confuses students in my experience. So I'm just going to distribute the positive 2 to each of the cells. And so I'm going to get 2, negative 2, negative 8, and 4. And now let's do the subtraction. So we get 9 minus 2. We get 21 minus a minus 2. We get negative 6 minus a minus 8. And we get 3 minus 4 for negative 1. And right now, the things in these cells, they have absolutely no meaning to us. Don't worry about them. We're just carrying out operations on matrices. Okay, so what do we have left? Well, we talked about equality. We talked about scalar multiplication. We talked about adding and subtracting and even combining these two elements. There's two other things I want to look at with you today. The first one is actually matrix multiplication. And the next one is something that Carl Friedrich Gauss came up with for solving large systems of equations by using matrix operations. Okay, so let's take a look at matrix multiplication. First thing I want to say about matrix multiplication is that while it's true, if the matrices, no, I can't even say that. So in order for us to be able, just to be able to multiply two matrices, the number of columns on the first matrix must equal the number of columns, number of rows on the second matrix. And this is how we would describe permission using English. However, most students find this kind of confusing to find their way through these words. So let me give you an example of what I mean. You might want to pause the video if you're still writing that down. Okay, So here I have 2 rows and 3 columns. So this is a 2 by 3. This 3 represents the number of columns. This matrix has 1, 2, 3 rows and 1, 2 columns. And so what we're looking for, what I wrote in all those words is these numbers have to be the same. In order to be able to multiply these matrices, these numbers need to be the same. Okay? And what if instead of doing, let's call this one matrix A, let's call this one matrix B, what if instead of doing A times B, that's this setup here, what if we consider B times A? So I would flip those matrices around, 1, 3, negative 1, 2, 0, 4, and 1, 2, 3, 4, 5, 6. Now I've got a 3 by 2 times a 2 by 3. And again, these numbers are the same. But if these numbers are not the same, then I cannot multiply these matrices together. And let's take a look at that. What if we change our B matrix to be 2, 4, 1, 0. There's B. So now A times B is going to be this 2 by 3 times this 2 by 2. Well, these numbers aren't the same. The number of columns in matrix A isn't the same as the number of rows in matrix B, so I can't multiply here. But what if we talk about B times A? What if we talk about 2, 1, 4, 0 times 1, 4, 2, 5, 3, 6? So this is a 2 by 2 times a 2 by 3. These numbers are the same, which means that we can which has a very interesting implication. Because A times B doesn't necessarily equal B times A. You know, almost all our thinking lives, 2 times 3 has equaled 3 times 2. We've had the commutative property of multiplication. 6 equals 6. We said it doesn't matter in which order you multiply these two numbers, you end up with the same answer. But with matrices, that's not always true. Sometimes we can't even do the multiplication. So that'll be something to watch out for when we do matrix multiplication. Now that we figured out what permission we need in order to multiply two matrices, what about the size of the product? How big will the matrix be when I'm done multiplying the two matrices together? So let's say I've got A equals 2, 1, 3, 6, and B equals negative 1, 4, 3, 0, negative 2, 1. And so I want to think about A times B. So A is a 2 by 2, and B is a 2 by 3. And yes, I can multiply them together. And these tell me the order of the product. So when I multiply A times B, the result is going to be some matrix that has 2 rows and 3 columns. This is going to be the result of multiplying A times B. And can we even do B times A? Well, that's a 2 by 3 times a 2 by 2. These numbers aren't the same, so we can't multiply them. But when we can multiply them, because the number of columns in the first matrix is equal to the number of rows in the second matrix, when these numbers are the same, these numbers tell us the order of the product. Okay, next, let's actually carry out matrix multiplication. Here's matrix A, 2, negative 3, 1, 4. And here's matrix B, 2, 3, negative 1, negative 2, 4, 5. Okay, and I'd like to multiply A times B. A times B. So that's going to be a 2 by 2 times a 2 by 3. Yes, they're the same, and this is the size of the product. So I'm going to make an oversized novelty. Make a big oversized novelty 2 by 3 matrix so that I can put all my work into these big cells. I find these big cells can also help me figure out what things should go where, like what things get multiplied by what things. Okay, so let's say I want to fill in this box. This box is in the top row and it's in the first column. Now, whichever matrix comes first provides rows, And whichever matrix comes second provides columns. So when I want to fill in this cell, I have to use things from the top row and the first column. Well, this one provides rows, top row, and first column. So what do? Well, I multiply 2 times 2, and then I add that to negative 3 times 3. 2 times 2 plus negative 3 times 3. And I get 4 minus 9, which is negative 5. If I want to fill in this cell, this one's in the bottom row and in the second column. So I'm going to use the bottom row, second column. 1 times negative 1, 1 times negative 1 plus 4 times negative 2. And so I end up with negative 9 in this cell. Oops, not in that cell. I was using the bottom row and the second column. 1 times negative 1 plus 4 times negative 2. Okay. What about this cell over here? It's in the top row and it's in the third column. Top row, third column, 2 times 4 plus negative 3 times 5. So we've got 8 minus 15, or negative 7. If I want to fill in this cell over here, that's again in the bottom row and in the first column. So I use bottom row and first column. 1 times 2, 1 times 2 plus 4 times 3. 4 times 3. And we get 2 plus 12 is 14. Okay, and if I want to fill in this cell over here, it's in the top row and it's in the second column. So I want the top row with the second column. 2 times negative 1 plus negative 3 times negative 2. And so I get negative 2 plus 6 is 4. And then finally, if I want to fill in this cell, which is in the bottom row and the third column, I want the bottom row times the third column. And so I'm going to have 1 times 4 plus 4 times 5, or 24. So my solution, my product, is this 2 by 3, negative 5, 4, negative 7, 14, negative 9, 24. All right? Well, I think it's your turn. Let's have you do a problem or two. Let's first consider, that's not what I want. That's what I want. A equals 3, negative 2, 5, 4. And B equals 2, 3, 6, negative 1, 4, 1, 0, 7. Okay, so first find A times B. If possible, I guess. That's what the directions say. Pause the video, take some time, find A times B. Okay, welcome back. So I notice that A is a 4 by 1 and that B is a 2 by 4. These numbers are not the same, and so I can't find this. All right, well, that's a little disappointing. So then let's ask about B times A. Will you please find B times A? Oh, by the way, pause the video and actually find it. So, welcome back. We know that this is a 2 by 4. This is a 4 by 1. And if I'm doing a 2 by 4 times a 4 by 1, these are the same, and this would be the size of the product. 2 rows and only 1 column. So let's make a big, oversized novelty. 2 rows, 1 column. That's all I get. So if I want to fill in this cell, I'm using the top row and the only column. This one, remember, the letter that comes first, the matrix that comes first, provides the rows. So I'm going to use these rows with this column. So I get 3 times 2 plus negative 2, plus 3 times negative 2, plus 6 times 5, plus negative 1 times 4. I get 6, I get minus 6, they cancel, I get 30 minus 4 is 26. And then, to fill in this, I'm using the bottom row and the only column. So I've got 4 times 3 plus 1 times negative 2 plus 0 times 5 plus 7 times 4. And so we've got 12 minus 2 is 10 plus 28 is 38. And so my product would be 26, 38. Okay, so we can multiply two matrices together. What about A equals 3, 0, negative 1, 0, 4, 2, 5, negative 3, 1, and B equals 1, 4, 0, negative 5, 1, negative 1, 0, negative 2, 3. And I want to do A times B. Well, I know that this is a 3 by 3, and this is a 3 by 3. These numbers are the same, so I'm just going to be making a big 3 by 3. So, let's make a big 3 by 3. I know you think this is silly to draw this big graphic organizer. My experience is students who do not do this get lost in figuring out what goes in which cell. So, if I want to fill in this cell, I know I'm on the second row, first column. This one provides rows, this one provides columns. So I want the second row, and I want the first column. I'm going to have 0 times 1 plus 4 times 4 plus 2 times 0. And I end up with 16. Okay, what about this one over here? It's in the top row and it's in the third column. So I'm using the top row with the third column. I'll have 3 times 0 plus 0 times negative 2 plus negative 1 times 3. And so I end up with 0 plus 0 minus 3, or negative 3. And if I want to fill in this box here, it's in the bottom row and the second column. So I'm going to use the bottom row and the second column. I'm going to have 5 times negative 5 plus negative 3 times 1 plus 1 times negative 1. And so I end up with negative 25 minus 3 is negative 28 minus 1 is negative 29. Okay, well, let's fill in some other boxes. I'd like to fill in this box. Will you please find what goes in this cell here? Pause the video. Give it a try. Welcome back. This is in the top row and the first column. So I'm using top row with first column. I get 3 times 1 plus 0 times 4 plus negative 1 times 0, or 3. And if I want to fill in this cell, it's in the second row, second column. So, second row, second column, I'm going to have 0 times negative 5 plus 4 times 1 plus 2 times negative 1. And so I end up with 2 there. And if I want to fill in this cell over here, I'm going to be in the second row and the third column. Second row, third column, 0 times 0, plus 4 times negative 2, plus 2 times 3. So I get negative 2. And if I want to fill in this cell, it's in the bottom row, first column, bottom row, first column, 5 times 1, plus negative 3 times 4, plus 1 times 0. And so I get 6 minus 12, or negative 6. If I want to fill in this cell up here, it's in the top row, second column. Why don't you figure that one out? Okay, welcome back. We're working on the top row, second column. I have 3 times negative 5, plus 0 times 1, plus negative 1 times negative 1. So that's negative 14. And then finally, to fill in this cell, it's the bottom row and the third column. So I'm using the bottom row and the third column. 5 times 0, plus negative 3 times negative 2, plus 1 times 3, and so 9 goes in that cell. And so then my product of A times B will be 3, negative 14, negative 3, 16, 2, negative 2, negative 6, negative 29, 9. And there's our product, A times B. But what about doing B times A? Well, there's a 3 by 3 times there's a 3 by 3. Yes, possible. Yes, a 3 by 3 will be the product. So let's now multiply these. And again, I'm going to draw this silly graphic organizer, this big blank 3 by 3. You don't have to. I find it helps me a lot. Okay, so this one is providing rows, and this one is providing columns. Some students find it useful to rewrite these two matrices so that the row providing one always comes first. Just saying, that's what some people have found successful. Okay, pause the video and then come back and you can see the answers. Okay, to fill in this cell, I'm in the top row and the first column, so I've got 3, 0, and 0. And to fill in this cell, I'm in the top row and the second column. I've got 0, negative 20, 0. And to fill in this cell, I'm using the top row and the third column. Top row, negative 1, negative 10, 0, negative 11. To fill in this cell, I'm in the middle row, the second row, first column. Remember, this one is providing rows and this one is providing columns. I want the second row and I want the first column. So 12, 0, negative 10 is positive 2. And here I want the second row, second column. So I want 4 times 0, 1 times 4 is 4, plus 6 is 10. And then I want to do this cell, which is in the middle row, third column. So I want the middle row again, and I want the third column. Negative 4 plus 2 minus 2 is going to be negative 4. And then finally down here, I'm using the third row, the bottom row, with the first column. I get 0 plus 0 plus 15. And then to fill in this cell, I'm still in the bottom row, but now I've got the second column. 0 minus 4 minus 9 is minus 13. And finally, bottom row, third column, I've got 0 minus 2 plus 3 is positive 1. All right, so with that being said, what about using my calculator. Well, I want to talk about using our calculator for this. So our calculator will happily do matrices for us. Here, there's a hello, little light. Wow, that's really dim. I really need to get me a bright color screen one. Hold on, let me see if I can get the glare from outside off of this. So let's take a look at using our calculator. All right. So I've got these two matrices, and I've got 3, 0, negative 1, 0, 4, 2, 5, negative 3, 1. It's matrix A, and matrix B, 1, negative 5, 0, 4, negative 1, 4, 1, negative 2, 0, negative 1, 3. Okay, and I want to do A times B. And we know that this 3 by 3 times this 3 by 3 should generate another 3 by 3. Well, the first thing we have to do is we have to get the matrices into our calculator. So matrix button is here under the math button, so it's above the reciprocal button, so second matrix, and we see that we have names, math, and edit. The first thing we want to do is edit this matrix. And here it's asking us, what's the order of the matrix? Well, our matrix A is a 3 by 3 matrix. And then we go in to type in the values that we see here. 3, 0, negative 1, 0, 4, not 42, but 4, 2, 5, negative 3, 1. And so matrix A is typed in, and we can quit out of that. And if we go back to matrix and pull up this name, just hit enter. See how it says matrix A here on our screen? If we hit enter, it shows us matrix A. Okay? We want to also get matrix B in the calculator, so go back to matrix, come down to B, and go over to edit, and you want to edit B. We also want to make B a 3 by 3. And so now we're going to type in 1, negative 5, 0, 4, 1, negative 2. Please make sure you use the negative button and not the subtraction button by mistake. Negative 1 and 3. Okay, so there's matrix B. And again, we could come over here, pick up the name, and see matrix B is correct. That should be negative 2, and it's not. So let's go back and edit. Oh, and notice this isn't 31 bracket. It's here's matrix B, and this is the matrix. So these are parentheses around the matrix. Okay, so let's go back and edit that matrix and change that 2 to a negative 2. Negative 2. Okay. So now we have matrix B the way we want it, we have matrix A the way we want it, and we want to do A times B. So here's what we do. We call up matrix A's name, we call up matrix B's name, we just put them next to each other because proximity means multiplication, and we hit enter. Ta-da! Matrix multiplication done. And what if we want to do B times A? Well, no worries, we just do matrix B, matrix A. Now we've got B times A. Ta-da! There it is. 3, negative 20, negative 11, 2, 10, negative 4, 15, negative 13, 1. So, wow, that's really fast on our calculator. I believe the ACT, you see matrix multiplication problems, but ACT is calculator active. So, duh, do this on your calculator. I think that makes a lot of sense. Okay, the last thing I want to look at with you today is solving systems using matrices. So let's take a look. Let's go back to last semester when we were doing systems. 3y plus 2z equals 1. X plus 4y minus z equals 7. 3x plus y plus 3z equals negative 2. And so what we said last semester was we'd pick two equations and we'd eliminate a variable. So 2x plus 3y plus 2z equals 1. And then I'd have to multiply everything here by 2. 2x plus 8y minus 2z equals 14. And then I would subtract, and I would get negative 5y plus 4z equals negative 13. And then I'd pick two other rows. 3x plus y plus 3z equals negative 2. And if this is a 3, I'm going to need to multiply this row by 3. So 3x plus 12y minus 3z equals 21. And again, subtract. 3 minus 3 cancels. 12 minus 1 is 11y. Minus 3 minus 3 is minus 6z. And 21 minus a negative 2 is 23. And now we're supposed to take these two and put them together. And so we get negative 5y plus 4z equals negative 13. And 11y minus 6z equals 23. So if I multiply this row by 3 and this row by 2, I'll be able to cancel z's. So top row by 3 is negative 15y plus 12z equals negative 39. And bottom row by 2, 22y minus 12z equals 46. And because these are opposites, all I have to do is add these equations. I get 7y equals 7, or y equals 1. And now that I know what y equals, I can plug this y back into either of these equations. So 11 minus 6z equals 23. Negative 6z equals 12. Z equals negative 2. And now that I know what y and z are, I can plug them into one of these equations. So, for example, into the top equation, 2x plus 3 times 1 plus 2 times negative 2 equals 1. And I get 2x plus 3 minus 4 equals 1, or 2x equals 2, or x equals 1. And we said last semester we would write this as an ordered triple, 1, 1, negative 2. So that's how we did the problem last semester. This semester, we've got matrices, and we've got Carl Friedrich Gauss on our hands. And because we have Carl Friedrich, we can use something called reduced row echelon form. Reduced row echelon form. And I'm going to show you this first on the calculator, because that's what most of you are going to do. But some of you might be interested in seeing, how's that work? What's he doing? And I'll show you that next. But because the ACT is a with calculator test, you should be able to solve this system and all the systems that you want to solve from last semester using reduced row echelon form. So let's type in this matrix. In fact, I want to say something about this system. We've got a couple of matrices here. First, we could talk about a coefficient matrix. And our coefficient matrix is just made up of these coefficients. It doesn't have any of the answers, just the coefficients. 3, 1, 3. We could also have an augmented matrix where we augment the coefficient matrix with the solutions. 1, 4, negative 1, 7, 3, 1, 3, negative 2. Okay, and actually I want to use this augmented matrix in our calculator using row echelon form. Now, row echelon form means we want to carry out a series of operations on this and put it into the form 1, 1, 1. And there'll be some numbers here and some numbers over here when we're in reduced row echelon form. I'm sorry, this is row echelon form. Reduced row echelon form, the one I want to use, looks like this. 1, 0, 0, 0, 1, 0, 0, 0, 1, number, number, number. And the reason I want reduced row echelon form is because I'll know that x equals this number, y equals this number, and z equals this number. And I can just read those numbers off of reduced row echelon form. I'll show you how to go from this augmented matrix to its reduced row echelon form by hand in a minute, but first let's do it on the calculator because that's what most of you are concerned about. I think I did a positive one here, yes. Okay, so we'll type in our augmented matrix, so go back to matrix, and we want to go over to edit, and we're going to edit A. Now we've got 3 rows, but 1, 2, 3, 4 columns. So this is a 3 by 4. And we'll type in 2, 3, 2, and then the answer 1. And then 1, 4, negative 1, and 7. And 3, 1, 3, negative 2. Okay, so now we've got this matrix, this augmented matrix, coefficients and solutions typed in. And if I come back over here to matrix, like I had to quit out, go to the main screen, and then come back to matrix, see how it says name, math, edit? Well, this time I want to go to math. That lets me do some math operations. And I want to scroll down. Look, here's a little operation that will tell us the dimension of the matrix, as though we couldn't count the rows and columns ourselves. It's kind of adorable. Okay, but for us, we want to scroll down until we not REF, but we want RREF, reduced row echelon form. Okay, and what do we want to do this on? We want to do this on matrix A. So we'll go to matrix A, and we'll hit enter, and look, x equals 1, y equals 1, z equals negative 2. Oh my God, that's so amazingly fast. Why do we make kids do systems by hand? And the answer is, I don't know. I don't have a good answer for you on that. All right, so let's see what's happening here. 2, 3, 2, 1, 1, 4, negative 1, 7, and 3, 1, 3, negative 2. By the way, if you're still watching, you don't need to keep watching in order to do the homework. You can do it, just pull out that calculator, go to town on it, because that's what you're going to see on the ACT. But if you're curious to learn about Gauss's method, then let's see what he was talking about. So he makes this augmented matrix out of the system. And remember, he's trying to get to 1, 0, 0, 0, 1, 0, 0, 0, 1, and then some numbers. Okay? And so he allows us 3 operations. And those 3 operations are: we can switch 2 rows. 2, we can multiply a row by a scalar. And 3, we can multiply by a scalar and add to another row. And so using only these 3 operations, we're going to turn this into that. But wait, it gets better. He gives us a little roadmap. He says, if you want to do this efficiently, start here. Turn this thing, whatever's in this cell, into a 1. Then use that to turn these things into zeros. Then come over here and turn this thing into a 1. And then use this to turn that into 0. Finally, jump down here and turn this into a 1. Once we've turned this into a 1, come up to these spots and turn them into zeros, and then use this to turn this into a 0. 9 steps. Now, I want to say that when I want to turn something into a 0, I can do this. Use this to turn things into 0, and I use these when I want to turn into 1. Okay, so first step is to turn this into a 1. Then I want to use that to turn these into zeros. I hop down here and turn this into a 1. I use this to turn this one into a 0. Not that one yet. Just this one into 0. I hop down here and turn this one into a 1. Remember, in order to turn stuff into a 1, I'm probably going to be doing multiplying by a scalar, but maybe I'll be switching 2 rows. Okay, and then I'm going to use this 1 to turn these into zeros. That's what this is for. And then finally, I'm going to use this to turn this into a 0 with this strategy. Okay. We've got a roadmap. We have some operations. Now, I want to turn that into a 1. I could multiply everything here by 1/2 and do 1/2 row 1. However, that would give me a fraction here and a fraction here, and I really don't want to do that. I noticed that I had another option for turning things into 1, and that was switching 2 rows. So I'm going to flip these 2. And so now I'm going to have, and I guess I could use some notation for that. Row 1 switches with row 2. And you might say, why are you writing down that notation? Well, inevitably we make mistakes, and when we want to go back and try and find our mistakes, it helps to know what we were thinking and doing along the way with each step. So I will write down what I'm doing for each step. Okay, next. I have to use this to turn these into zeros. So I'm going to do -2 row 1 plus row 2. Now, this is kind of like the Hulk. It temporarily changes row 1. And then that temporarily changed row 1, Bruce Banner turns into the Hulk, has an effect or impact on row 2. Row 1 goes back to being Bruce Banner row 1, but row 2, that car is forever changed by the encounter. So what's going to happen here is this row will end up being the same, and we're going to do -2 times this plus this. -2 times this is -8, plus this is -5. -2 times this is 2, plus 2 is 4, And negative 2 times this is negative 14 plus 1 is negative 13. Okay? We could also do, because remember we want to use this to turn this into 0, we could do negative 3 row 1 plus row 3. So negative 3 times this plus this. Negative 3 times this is negative 12 plus this is negative 11. Negative 3 times this is 3 plus 3 is 6. And negative 3 times this is negative 21 minus 2 is negative 23. You may remember this as our two variable equations. Okay, now we're supposed to turn this into a 1. Now I could flip these two rows, but I don't see any benefit in moving this one here. That doesn't turn that into a 1. And so really the only recourse I have is negative 1/5 times row 2. So now I've got 1, 4, negative 1, 7, 0, 1, negative 4/5, negative 13/5. I know, fractions, ew. And 0, negative 11, 6, negative 23. Okay, and now I'm supposed to use this to turn this into a 0, and so I'm going to do 11 times row 2 plus row 3. Okay, so 11 times row 1 is going to stay the same. Row 2 is even going to stay the same long term, and it's just temporarily going to change. And we have negative 13/5. And then we've got 11 times this plus this. 11 times this plus this. 11 times this is negative 44/5 plus 6 or 30/5. So that's going to be negative 14/5. And it's looking grim. I see that. It's not a 1. Kind of sad. But don't worry, it'll all work out. Okay. And then I want to do 11 times this, which is 143. I don't know, 11 times 13. Yes, 143. So I've got negative 143 over 5, and I want to add that to negative 23. Well, negative 23 times 5 over 5 is negative 115 over 5. So, adding negative 115 over 5. And was it negative? They were both negative. I did negative 1/5. Oh, negative times negative, that's positive. And you gotta check up on yourself. So that's positive. And so now we add these together, and we've got 143 minus 115, and that gives me 28/5. Okay, so there's 28/5. All right, so what do we do next? Well, Gauss says we're supposed to turn this into a 1, and I'm not going to be switching two rows, so I'm going to multiply by a scalar here, which means I want to do negative 5 over 14, row 3. And when I do that, 1, 4, negative 1, 7, 0, 1, negative 4/5, negative 13/5, and finally 0, 0. If I multiply this by this, I get 1. And if I multiply this by this, I get negative 2. Now, Gauss stops here. Gauss stops here and says, ugh, I'm tired. And I know that z equals negative 2. And he says, great, I know that z equals negative 2. Let's do some back substitution and find y and x. So he looks up here and he says, y minus 4/5 z equals negative 13/5. And so he plugs in z equals negative 2. Y minus 4/5 times negative 2 equals negative 23/5. And he comes up with y plus 8/5 fifths equals negative 23 fifths. And that didn't work for some reason. That's correct. And I erased the, oh no, I've got it here. That looks good. Becomes that 1 minus 4 fifths. Negative 4 fifths times negative 2, positive 8 fifths. Oh, because I can't subtract. So y equals 15 fifths, or 3. No, y doesn't equal 3. Y equals 1. So I've made a mistake somewhere, and I'm very sad. Why does that say 23 when it should say 13? There we go. Okay, and so now I end up with 5 fifths. Negative, no, because I'm going to subtract. Sighing, deep sighing, deep sighing. I already, luckily we already know the answer is this. So, that's 8 fifths. That's negative 13 fifths, which would be negative 21 fifths, and I don't want that. This must be the same sign as this. I need this to be positive. Did I miss something up here? When I multiplied by 1/5, I think I did, sigh. And since I've erased it, and you can go back and see if I made that sign mistake, but I can't go back. Well, anyway, when I plug in, I should get a 1 here, because we already solved it and we know it's a 1. And it kind of sucks to do this much work and still make a mistake, because, yeah, a lot of people will make a small sign mistake, not unlike the one I made, and say y equals this. And we know that y is not equal to that. Okay, so Jordan, not Gauss, but Jordan comes along and says, this is good, but if you're going to make a commitment to this process, why don't you go all the way and turn these into zeros, and then use this to turn these into zeros. And that's where we get that full 9-step roadmap. And when we use Gaussian elimination, well, Gauss-Jordan elimination, that brings us to reduced row echelon form, which would eventually lead us to 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, negative 2. Had I not botched that up. I'm not going to take the time to go back and rewrite this on this small board. So if you're intellectually curious, by all means, there's plenty of problems in the book that ask you in section 8.1 to solve systems with reduced row echelon form, or even row echelon form. That's what Gauss came up with, and then do the back substitution. But I'm just going to say, that was that age, and in this century, do your reduced row echelon form on this magic box. So, those of you still with, here's one to try. X, negative 2y, 3z equals negative 7. 4x plus 5y plus z equals 4. Negative x plus y minus 2z equals 5. Okay, so either by hand or with your calculator, solve this system using reduced row echelon form, or I guess if you want, row echelon form with back substitution. Alright, give it a try. Come back in a few minutes when you're done. Welcome back. I'm going to type this matrix in. It's a 3 by 4. 3 by 4. I've got 1, negative 2, 3, negative 7, 4, 5, 1, 4, negative 1, 1, negative 2, and 5. So if I'm using my calculator, I want to go to Math, and then I want to scroll down to Reduced Row Echelon Form, RREF. Notice here below that we have row swap, row add, and then multiply a row, and multiply a row, and add the row. So here we've got Gauss's operations built into our calculator if we want to do this by hand. I don't. I just want reduced row echelon form, but not there. You have to quit out. That's going to be a 5. You have to quit out and do this on the main screen. Matrix, math, reduced row echelon form for matrix A. And there we go. We've got x equals 6, y equals 5, and z equals 3. Is that a 6 or a negative 6? It's a negative 6. Okay. And so as an ordered triple, negative 6, 5, and 3. Great. Welcome to Matrices. Tomorrow, we're going to talk about the determinant of a matrix, how one number can represent a matrix. Have a great day, everyone. Oh, assignment number 1 goes with this on your Matrices unit assignment calendar.